it's indeed a delight to be able to address you guys as part of the India Science Festival. I've been involved with science festivals for a while now, especially with the Edinburgh International Science Festival, which is one of the kind of oldest science festivals in the world. But in a way, trying to do the same thing in the country where I come from, I think I find it, again, an honor, and I think it's been a while since I've wanted to do this. So thank you for organizing this. And today's session is, I mean, this is a nice segue from the last speaker's topic on science fiction to the future of robotics. So robots have been around for a while. It's such a fast moving field, and it's very hard to keep up with the new developments in robotics. So this is an attempt at trying to show you where robots have traditionally been useful and where the new trends in robotics are going, and perhaps even speculate the areas in which different kinds of robots can play a big role in affecting different walks of our life. So I'm pretty sure many of you have seen robots in very classical applications, like a car manufacturer or in working in an assembly line in a factory. But actually, if you look at the screen, the majority of the little sort of images I've put up are robots or applications of robotics in domains that we would not have considered previously, maybe even just 10 years ago, as something where robots could play a big part. So we've known that robots have played a big part in the space station, the building of the space station. Robots are increasingly playing a bigger role in manufacturing of smart cities and autonomous driving cars, but also in the for essentially giving us food security in terms of being more productive in doing weeding and agriculture. There's also a big push in the use of robots in the medical industry, but also to deal with challenges in the aging society, but also in prosthetics and exoskeletons. So there's a whole range of robotics applications, and I'm not sure if how many of you in the audience recognize this kind of figure on the top third, the one I have the pointer on. That actually is inside the core of a nuclear power plant, and one of the challenges involves robots for decommissioning of our nuclear power plants. So these are all very exciting challenges for robotics to solve, and I just want to kind of give a perception of where traditionally robotics has been and where we're going with it. So traditionally, robots have always been programmed by either teleoperation, in other words, getting the robots to mimic a program or a particular sequence of movements and repeat it again and again. So the new research in the labs around the world have been pushing this towards getting robots to act more autonomously. In other words, start making decisions on their own, start creating scenarios where humans can be significantly out of the loop and don't have to interact with the robot on a very, at a time scale which is on the order of the real-time operations. But the real challenge, while we wait for autonomous solutions, is somewhere in between, where we can seamlessly move between fully autonomous sort of challenges to fully teleoperated settings. And really, I think so one of the things that we are trying to do is see if we can get robots to autonomously behave in a way that is challenging for different applications. So let me try and do one of the. I'm getting a small. Let me try and move this cursor away so that you're getting the full slide. I hope this is a bit of a challenge, a technological challenge that I'm going to try and fix. Let me see if I can. So I don't think I can move this completely out of the way, but I'll try and adjust it in a way that it is not taking up big parts of the screen. Okay, good. So if you think about why we want to deal with collaborative and shared autonomy rather than fully autonomous behaviors, there are some interesting scientific challenges. So for example, for fully autonomous behaviors to work, we cannot be dealing with situations where there's close interactions with humans, when there's noising and ambiguity in the sensing, or if there's situations where we've got real world dynamics to deal with. And more often, the unmoral user intentions are another big challenge. So, and these are all challenges that you may face while we are dealing with prosthetics, self-driving cars, underwater robotics, inspection and integrity management in offshore oil and gas platforms, etc. Now, in addition to these scientific challenges, there is a socio-economic reason why we want to use robots of these kinds to deal with these things. And one of the reasons is because we are trying to address some of the grand challenges, like improving the efficiency of man-machine teams to meet the industrial demands, to ensure food security, but also we are increasingly seeing acid inspection needs in offshore oil and gas platforms, in the nuclear industry for decommissioning. Also, there's a big challenge in healthcare and aging in our society for exoskeletons, but also flexible redeployment in emergencies like the pandemic. So we are looking for low-touch economy and social distancing for co-work. So the idea is, can we do these things while we are ensuring that we're able to deal with these things efficiently? So let me start by giving you a quick example of how these robots are working, especially how we can use shared autonomy for remote operations. So on the screen, you're seeing, you're going to see a video of a robot screen on the right that a person using the robot is going to see. On the left will be the actual live image of the robot operating in another room, another environment. And what you're going to see now is, and what you're going to see now is this image of the console that a person is seeing while the robot is operating autonomously, while the human is giving the high-level goals or the volition of where to go, where to move, how to avoid obstacles, etc. So the thing to note here is that it is not the human who is deciding which wheels to move, which motors to move, which hands to use, but it's the robot autonomously deciding for itself. The human gives a high-level volition of which object to pick and where to place, and all of the low-level decision-making happens at the level of the individual robots at the site. So this is extremely important because often we don't have a direct line of sight. There is no, there is an issue with transmission delays. There's an issue with a potential networking failure. So autonomous behaviors help you deal with those challenges on the fly. And we do think that some of these challenges can be usefully deployed in domains ranging from nuclear and offshore decommissioning, things like disaster recovery, things like collaborative manufacturing, remote operations of heavy machinery, etc. So, so these are the kind of portfolios of the research projects that we have in our lab that we use shared autonomy for. And indeed, one of the things I want to highlight, one of the projects that I want to highlight is something called the Orca Hub. And this is offshore robotics for certification of assets, particularly in the offshore oil and gas industry. So some of the things that we've been looking at is how can we use legged robots to do offshore asset inspection. So you can probably see a video now of the robot actually operating in an environment that is very hard for wheels to operate. So it's got obstacles, it's got to step over obstacles, it's got to climb steps, and the idea is not just for robots to go and map the environment and sense the world, but be able to operate equipment, turn valves, push buttons, take sensor readings on the fly while it's operating in very complex environments like these. And indeed, not just, and it doesn't have to be limited to quadruped robots. It can be wheeled robots where the robots are autonomously operating and deploying things like sensors on a sort of field, which is monitoring, in this case, monitoring corrosion in an oil tank, for example. So these are examples of scenarios where robots and humans want to operate in a cohesive way while robots take a lot of decisions on its own. The other big challenge that we've been looking at, and one of our flagship projects is with the NASA, with the Johnson Space Center in Houston, where so one of the challenges is, can we use robots for not just International Space Station deployment, but on future missions to Mars? Can we use robots as a way of creating assets on the surface of Mars before astronauts arrive, or can we also use these robots as a way of maintaining assets when the astronauts are not on the surface? So if you think about it, so what are the kind of capabilities that we may need for robots like these to operate efficiently? So we don't think of when we talk about extreme environments, we don't think of space, but space is an extremely hostile environment where astronauts are doing spacewalks because they have to, not out of choice. So this is where we're trying to build capabilities equivalent to a human being. So things like walking on uneven terrain. So what you see in this video here is a humanoid NASA Valkyrie robot in our lab being trained to walk on uneven terrain using onboard sensing. So you can see on the right the kind of LiDAR-based sensing that the robot sees, and then it decides for itself where to step, how to step, and how to maintain balance. So one of the challenges is, how do we do multiple hierarchies of tasks while the robot is trying to maintain balance? So maintaining balance is a priority, while sort of reaching and grasping for objects is a secondary task that it needs to fulfill. So those are the kind of the scientific challenges that we're trying to address and operate with. So it's not just in the space industry, we're also looking at how we can use robots for the manufacturing sector. So we have a project with the Honda Research Institute, which basically is for help robots and humans working together to lift heavy loads, weld, do accurate positioning. So for example, some of the works that we've been doing in collaboration with Honda involves simulating both a robot and a human and its interaction, and look at how we can get this on real hardware. So how can, as a prototype, how can robots and humans work together to manipulate objects of interest? This is a very challenging job, because you have to understand the intentions of the humans, but also do optimal behaviors that are critical, time critical. It is very different from a robot, like a wheeled robot sitting on the ground and moving on an intermittent basis. This is a real-time control with very high frequencies. And where do these things kind of play a big part? These things can play a big part in increasing the flexibility of manufacturing settings. So traditionally, if you look at how large aircraft hangars or factories work, you've got large fixed jigs. Now we are already seeing robots and humans working side by side, but not necessarily together. The future is where we marry the best of both worlds. We marry the precision and accuracy and load capabilities of the robots while we use the decision-making capabilities of the humans, so contextual decision-making of the humans for doing, things like fitting of large parts in collaboration with the robot. Okay, so I want to slightly switch tack and talk about robots in a slightly different domain. So another domain where we've been working with and the use of shared autonomy is in the area of healthcare. And here's a collaboration with some companies like Touch Bionics and Honda, where we've been looking at upper limb prosthesis, but also lower limb prosthesis for effectively helping patients who've either lost a limb or have had some sort of injury, either a sports injury, or say somebody who's had a stroke and is recovering from post-stroke rehabilitation, for example. So let me see if I can get this video to you. I'm just trying to see if we can get this tab to move off. It seems to be quite annoying, but I'm not sure there's an easy solution to that. Okay, no worries. So one of the things, as you can probably see, the video here on the right is in our lab. We have a prosthetic, a person wearing an exoskeleton, which is applying forces on their legs, and in doing so, you can use it for helping them walk, say, up a slope, so that the person feels as if you're kind of being assisted while walking, or it can be used for rehabilitation settings, as I said before. The real scientific challenge is, how do I coordinate the movement of the humans and the exoskeleton in a way that it is not disruptive, but actually is helping the person in this task? And you will see some part of this live at the end of this talk when we go live to the lab. So now let's we've always science fiction has always been inspiring. We've always seen movies like the Iron Man, where we think about the future of work, where you're sitting in the comfort of your home and controlling multiple robots, multiple devices in remote locations. So although this was a science fiction, so I think this notion of using robots effectively is becoming increasingly more realistic, increasingly more real time and real life. And there are some, of course, there are some scientific challenges in addressing that, and I'm going to try and point out to few open scientific challenges, underlying open scientific challenges that I want to try and point out to. So, for example, we do need to worry about safety in these settings, especially when humans are involved. So we need to ensure that in hardware you've got compliant actuation, in software we've got real-time adaptation to be able to ensure that when robots and humans interact, they are safe. For that, we've been building lots of variable impedance actuation mechanisms, so robots that work efficiently on the fly with adaptation, with soft compliance in the loop. This second challenge is what we call reducing the sim to real gap. So, for example, getting digital twins to work, where we can get robots to be as close as possible to realistic simulations, so that we can do a lot of learning without really having to run the robot, while the real world physical simulations match this. And lastly, I think one of the crucial elements of robotics is trying to build systems that are verifiable and explainable. And this boils down to the fact that if something goes wrong, can we understand why something has gone wrong? What is the reason behind the failures, and be able to fix it? And this, it becomes even more poignant when we are using adaptive and learning systems. And what we've done is we haven't fully addressed all the socio-ethical questions in this talk. I don't have the time to cover all of these things, but I do want to reassure you that in doing the science that we do, we have been asking some very poignant questions about moral, ethical, and decisions that needs to be made while developing this kind of technology. How do we ensure responsibility and explainability? How do we transfer control between a robot and a human, and how do we do that seamlessly? And how do we deal with issues that arise out of learning systems that constantly adapt? And in order to do that, we've been looking at doing this through a couple of our initiatives. Both at the University of Edinburgh, and as part of, I'm a co-director of the Alan Turing Institute, which specifically looks at some of these moral and ethical decision-making in technology. And if you're interested, if you now go to the Wired UK website, there are a couple of videos. There are 4 subparts of a documentary that has been shot by Wired UK, which exactly addresses this problem of technological advances and the biases and the moral and ethical questions that we have to ask in order to, while we're developing this technology. So the last thing I want to sort of briefly address is, in trying to do all of these things, the way we've been doing this is by setting up a large center. It's called Edinburgh Centre for Robotics. And this is not just about science. This is not just about technology. It's about taking novel ideas and scientific ideas from innovation in labs to market through high TRL level, high technology readiness level ladders, through world-class assets and skills, and working with government and lawmakers to make this happen. So do check out the Centre for Robotics. So what I'm going to do next is to stop by quoting one of my favorite authors, Arthur C. Clarke. And this quote is very poignant in the field of robotics. We tend to overestimate technology in the short term, meaning we are always kind of overhyping the impact of robotics. And that can be a big problem if you're not careful about the limitations, or understanding the limitations of this technology. But at the same time, often we underestimate technology in the long term. So indeed, robotics is going to play a huge part in how we are going to live our lives in the next decade or so. And if we don't understand and study the impact of this technology, both in terms of jobs and skill sets, etc., then it is going to be challenging to address that at a later stage. So with that, what I'm going to do next is to show you a 5-minute video of our lab and the different things that we do in our lab, which will give you a nice segue into the live feed that we're going to get into after this. And then we'll have some options for some Q&A. So 5-minute video coming up, showing you all the different kinds of scientific challenges we address in our labs, in the words of the scientists, the postdocs, the PhD students, the faculty members involved with this. So let me try and play that.
Welcome to the Statistical Machine Learning and Motor Control group at the University of Edinburgh. Here we do exciting, world-leading research on robotics, machine learning, and data-driven techniques using artificial intelligence to make robots a lot more versatile and adaptive to the real-world situations. We do work across domains, so applying the core problems in robotics and machine learning to domains in oil and gas, transport, healthcare, as well as things like the challenges of exploration in outer space.
We want our robots to be autonomously deployed in industrial plants, for instance, to perform inspection tasks, to accomplish tasks that humans can't do or that are dangerous for them.
Our main business is to educate the next generation of outstanding postgraduate students and conduct cutting-edge research.
My research is focused on designing exoskeleton controllers that can assist people completing tasks such as walking. And to achieve this, what we do is we build quite complex neuromuscular models of human subjects and combine this with a very detailed set of motion data that we can collect in our gait lab.
We hope that with this setup and combining robotic assistance with electrical stimulation, physical therapists can have a tool to personalize the intervention and improve the outcomes of physical therapy.
My research is about robot localization in changing environments. When the robot's view is nearly occluded by large moving objects.
We want the robot to learn which objects are of interest without requiring a human to provide information about the shape or the visual appearance of these objects.
In order to enable robots to move while in contact, for example, when wiping a table or pushing a heavy object, my research focuses on how to plan or how to learn those types of physical contact interactions.
We are developing mathematical models to enable a robot to capture heavy and moving objects with two arms. At the same time, we are handling impact.
My research involves both humans and robots, where first we enable robots to predict humans' intentions and actions, and we also generate safe robot actions in order to help the humans reach their goal.
In construction, robots are often operated by humans in dangerous environments, needing expensive training. To reduce the operator burden, I'm working on shared autonomy, which combines human input and autonomous methods so the human can best utilize their expertise.
I'm really interested in human-robot collaboration, so how we can enable robots to perform a common task effectively with humans, such as pouring a wine into a human's glass. But humans are really difficult to predict, and so I'm interested in how we can better make those predictions.
I'm working on the development of robots that can be easily taught to manipulate objects and potentially collaborate with people or assist people in need just by giving a demonstration of the task.
I'm working on leg robot to make them traverse challenging terrains. The idea we propose is to start with a capable controller that already works on the robot and try to extend and add capabilities to make the robot cross challenging terrains.
I'm working as a software engineer in a field robotics lab, and also I'm doing some research about quadruped robots. I'm working on how those robots with 4 legs should plan their footsteps considering the torque limits on their legs.
When robots have to perform manipulation and walk simultaneously, they face a lot of uncertainty. One way we can increase the robustness of the system is by taking into account the capabilities of the robot, so its motors and also the contact stability.
There are many conditions that we cannot predict. For instance, when we are navigating in an offshore platform, we might encounter a floor that is wet. A way of dealing with this kind of uncertainties is by replanning quickly new motions.
I'm working on building better robots for specific tasks. So a robot that walks might need to be built a little differently than one that jumps. And so I'm working to create algorithms that modify the designs based on the tasks. And I'm looking at making those more efficient and physically realistic.
My work focuses on motion planning, especially when it comes to the environment changes that are in and out, or the objects that the robot is trying to pick up and move are moving. And this is especially useful when working with robots that need to be safe around people and other robots.
So the environment may have many different inclined slopes, and this gives rise to a lot of different options of when to place the foot and where to place the foot.
Robots in the real world have to operate in environments where obstacles around them are moving. So whether that's in hospitals where we have people moving around, or whether that's in a factory where you have other robots that you might need to avoid. My research interests are in developing algorithms and motion planning software that will allow us to move robots in ways that avoid those obstacles.
I've particularly enjoyed working on the large-scale projects which we have within the group.
and helping with the project management side with the Alan Turing Institute, the ISCF hubs, and also the EU Horizon 2020 projects.
So if you've liked some of the research that you've seen in the video and would like to work on some of these exciting platforms and projects, please do get in touch with us, and we'd love to have you as part of our team.
Okay, excellent. So I hope you guys have managed to see the video, and you've got an idea of the kind of the breadth of the applications of robotics that the lab works on and also the community works on, and perhaps it might have given you some ideas about, or interesting questions about things that we need to worry about and talk about as part of this, building new kinds of robots, new ideas where robotics can be kind of applied. So what I'm going to do now is to stop sharing my screen, and at some point, yes, I think that should work. And I'm going to try and ask one of my postdocs in the lab to start sharing his screen, and so that we can go live to the lab, where I will introduce to you very briefly some of the, let me see if we can get the live feed from the lab. We can try and see if we can see some of the demos, especially of the humanoids and of the exoskeleton stuff. So we may be experiencing some technical issues with getting the camera going. So let's see. Okay, good. Okay, so let's try. Vlad, are you ready to?
Yeah. Oh, it's not share the screen. Hello?
Yeah, hi Vlad.
So we are here, we are ready. You should be able to see our video now.
So maybe the right thing to do is to, the video is showing up on the side as a small thing. So maybe you should stop sharing the screen. Are you sharing the screen? You should stop sharing the screen.
Yeah. Okay.
So I'm seeing your sort of desktop, and we should not see that.
There we go. This should be getting better.
Yep. Perfect.
Excellent. Thank you for your patience. Welcome.
So yeah, so let me start by quickly introducing the first of the demonstrations. It's a humanoid robot called Talos, and the idea is we're going to try and show you the different bits and pieces of the work that we do with Talos. Over to you, Vlad.
Thank you, and welcome to the Field Robotics Lab. So our first stop today is the Talos humanoid robot. This is actually one of the most complex robots we have here in the lab. So what you're looking at is a robot the size and the shape of a human. You can sort of see compared to me sort of the scale of this. This brings itself a lot of difficult problems to solve. We have over 30 motors that we're controlling here in coordination, the whole body. We have a inertia and acceleration measurement on board of this robot. We've got a vision system with cameras and speakers up in the head. We've got sensors for forces, both in the hands and down in the feet. We do have 2 computers on board, and we have a Wi-Fi communication with the robot. So what we've been trying to do is to program robots like these to do whole body motion, to allow them to sort of the same kind of dexterity that people have when they perform tasks. And you can see here that we get the robots to coordinate its whole body. We've got some level of stability. We are trying to develop motions and code for this platform so that we can eventually take this out of the lab. But as you see at the moment, we are at a stage where we are developing this in a safe environment. That's why we have sort of a harness around to keep people safe. But eventually, we would like to take these robots out of the lab. So I'm going to step a little further, and we're going to do some walking as well. These are some of the hardest problems in robotics, to make sure that we can get not the robot not only to understand where it is and what it's doing, but also to robustly perform different motion and keep working in the environments that we work in. Yeah, let's try a little bit of walking. There we go. Yeah, so here you see we have the robot walking. We still have it balancing, coordinating the whole body as it is. So a lot of the work that we do comes down to sort of autonomy or punctuated autonomy. So this is the kind of interaction where you let the robot decide a lot about what it's doing and how it's going to do. And in doing this, we have learned a lot about how to control and how to design the motion for it. So we use a lot of ways how to model the robot using mathematical equations. We use a lot of kinematics and dynamics and Newton's laws of dynamics to model what the robot is doing. And then we write software that allows us to plan and generate this motion and also in real time correct for this. And by doing this, we have learned a lot about how humans move. So the next thing that we do with this is then look how we can transfer this onto other robots that we can wear, where this control is actually shared closely with a human. For example, an exoskeleton that can help us rehabilitate. So I'm going to hand over to one of my colleagues, Daniel.
So yeah, while Vlad's doing that, just a few things to add. I think people might ask, often there is a question, why the humanoid form? Why don't we put wheels, and why 2 legs? Why not have 4 legs or things? And the idea is, by challenging ourselves to do very complex problems like maintaining balance in real time, we are trying to push the boundaries of what control systems and sensing can really hit. And the exact same solutions can be transferred to, for example, the autonomous driving domain, where we need to react very quickly. If the motors need to react very quickly to a sensor of a person stepping in front of an autonomous driving car. So these problems are quite related. Over to you, Daniel. So yes, now what Daniel is going to explain, along with so Daniel's a postdoc student. It's a postdoc with us, and what Daniel is going to explain is the exoskeleton, the hip, knee, and the ankle exoskeleton that Andreas, one of our PhD students, is wearing. Over to you, Daniel.
Thanks, Sethu. Yeah, so as Sethu was saying, one of the things that we're interested in the lab is how we can use robots, but also exoskeletons, to assist humans in assisted living environments. So exoskeletons, like this one that you can see here, are robotic devices that are worn externally to the body, that are used to apply forces onto humans to assist them while they're completing motions. So typically exoskeletons will have a number of motors, like these that you can see here on this exoskeleton. And these are responsible for generating forces and torques. And those forces and torques are then transmitted from the robot to the human body via some attachment mechanisms, in this case, these straps that you can see here. And as Sethu was saying, this exoskeleton in particular has 6 motors, 3 on each side, assisting the hip, knee, and the ankle joint. So it's capable of assisting the full kind of spectrum of lower body locomotion simultaneously.
And maybe, Daniel, you might want to add the amount of torques these things are capable of generating.
So the amount of torques, it varies depending on the kind of exoskeleton you're looking at. But this one, which is quite a powerful exoskeleton, can go up from, I think the maximum torque is around 100 Newton meters. Typical torque should be 30 to 50 Newton meters. And so these types of exoskeletons that have the full range of lower body motion can be used for very intensive tasks, like, for example, assisting paraplegic patients who might be kind of paralyzed from the waist down. And another kind of key aspect of exoskeleton systems are the sensing capabilities that they have. So typically, these include encoders that are embedded in each joint. So in our case, we've got joint position and joint torque encoders in these joints, which allow us to get real-time information as to the torques and positions of the joints as Andreas is walking here. And this exoskeleton also has pressure sensors on the soles of the feet, so that as Andreas is taking steps, we can detect when he's making stance phase with the ground. And one of the big challenges for us as exoskeleton researchers is how we can use the information from exoskeleton sensors and other sensors that we have available to inform us of the correct kind of timing and magnitude of assistance to perform, so that we effectively assist people as they're walking or completing other motions. And the aim of our research with these devices is to eventually design controllers which can safely assist people who need it. So, for example, this could include the elderly or people with mobility issues. And in addition to that, we're also looking at how we can, in addition to helping kind of patients, also reduce the physical strain on healthcare professionals like nurses and physiotherapists, so as to reduce the chance of injury in the workplace. Oops. So that's everything for me. I don't know if you have anything to add.
Yeah. Thank you, Daniel. That was very useful. And I think we're going to move to the next station where we're going to look at some robots for reconfigurable factories. But while we're doing that, one more thing to add is that the exoskeletons, we think of it as assisting humans or people who are, injured or sick or stroke. But in theory, they can also be used for factory workers who are perfectly healthy but are doing very heavy repetitive tasks. So you want to take the load off their backs so that they don't face long-term injury. So some of the work that we've been doing, especially with respect to collaboration with Honda, is on using these kind of exoskeletons as a way of ergonomic, encouraging ergonomic behaviors in factory workers, but also assisting people who use heavy tools. Excellent. Now let's go to the sort of third station, where Christian's going to try and tell us a little bit about this upper body dual arm humanoid used for the reconfigurable factories of the future. Over to you, Christian.
Hi. So this is the next stage robot, and so you see that the upper part is the humanoid base. So this robot has two 6 degrees of freedom arms, and it has an additional degree of freedom for the rotating the torso. So this is used to interact with the environment. So we can pick up objects and place them somewhere else. At the end of the arms, we have two end effectors. You see that those are flat end effectors. And you can imagine that when we want to pick up objects, it would be done with basically with the palm, and you can pick up smaller and larger objects using this. And so this robot is usually used in a factory, and we are using it in a project which we call the Smart Reconfigure Factory. And the idea behind this is that you can build up a factory line, for example, with this conveyor belt here and tables, without the need to predefine where the conveyor belt is, where the tables are. And also when you interact with objects like this box, you don't have to predefine how this object looks like. So the idea is basically that you can move the robot into a new environment, place the conveyor belt there and the table, use new objects, and you don't have to specify all this, and can continue with your typical pick and place task in the factory. I'm now going to demonstrate how this pick and place task works, and I will talk a bit through the experiment. Oh, sorry, I forgot to mention, of course, so it has a color and depth camera on the head with which it can observe the environment. And by rotating its torso, it can, of course, map the rest of the environment. With this camera, it is observing this conveyor belt, and if I turn on this conveyor belt now, you see that the conveyor belt is moving, and the robot is observing this conveyor belt. Now, if I start the experiment, you see that the robot is adjusting to observe the conveyor belt. Now, it has never seen this object before. Now, if I place this object on the conveyor belt, the camera is detecting this motion, tracking this object, and once I stop the object, the robot will know that this is the object it should grasp, and I will just acknowledge this. And now it will go with the hands towards the object to grasp it from the conveyor belt and place it on the table. And in this smart Reconfigure factory, the idea is now that at the end of the table, we can have a human that interacts with the robot, and the robot would slide the object towards the human. So in order to safely interact with the human, so that these workspaces don't collide, but we can still enable a collaboration between humans and robots. In future, sorry,
no, that's okay. Yeah, I was going to just bridge this. Thanks, Christian. I was going to say that I think one of the things that the sort of scientific challenges in these kind of settings is we can move the robot around or the belt around or the table around, and still, because we are doing live sensing and live modeling, we can actually get the robot to react to these. This is in contrast to factories where you have to very precisely calibrate everything ahead of time and get everything to work fixed to a particular location. The moment the calibration is off, the pick and place goes wrong. So that is where the kind of adaptation from real-time sensing happens. Back to you, Christian, on the mobile-based stuff.
Yeah, so the core scientific part of this project here is that we don't want to provide how the objects look like. So we want to make this dynamic. In future, we would like to extend this to this mobile platform where the robot is not static here, but it can move around freely in the factory. For example, to autonomously pick and place objects somewhere. And on top of detecting these objects, what has to be done there is that the robot needs to be able to localize it. So it not only needs to know what the objects are and where they are, but it also needs to know where the robot is itself. In addition to this, it needs to avoid obstacles when it's going from between places for pick and place tasks.
Thanks, Christian. I think we need to move on in the interest of time. So the last station that we're going to get to is the quadruped. It's actually exciting technology where we're going from wheels to robots that can walk on 4 legs and manipulate. I think in the interest of time, we're just going to show you a very, very short demo of the robot actually reaching for a valve and operating it. So let's see if that is working. Let me.
Hello. So
hi, Eric. Yes, go ahead.
Hi. So here in this part of the lab, we have a quadruped robot that has been mounted with a Kinova arm, and we also have a scaffolding mock-up as like an oil rig. And this mock-up is useful for us to test things that are challenges for the robot in the real world. So it's simulating, for example, an offshore platform in the sea where the robot has to operate. And usually these kinds of quadruped robots, they have 4 legs, as you can see here, and they can walk around. And recently they are being used for inspection and maintenance operations where they have sensors to walk around these offshore platforms and see whether there's something that has broken and needs intervention. However, we are going an extra step further and putting an arm on top of it. So the robot can not only walk around and inspect with its sensors its environment, it also has the capability of manipulating that environment. And we have like a couple of props here, like a hand wheel, which the robot can turn, a lever, which the robot can pull, and a bunch of other tasks that mimic situations that the robot would be need facing in real life. Unfortunately, we are having some technical issues, so we had prepared the demo, but it's not working. So I apologize for that.
Okay, no problem, Eric. Are we not doing the arm either, right?
No, unfortunately, we just had a technical issue and it's not working. But I'm happy to answer any questions. Yeah.
Yeah, no problems. Yeah. No, anyway, I think we're running a bit out of time, so I think we should move on. So thank you all. So thank you everybody in the lab for that demo. We've seen some videos. I'm very happy to now open the floor for some questions and pass it back to Shruti. Yeah, over to you, Shruti.
Thank you so much, Professor. That was really lovely, and I must say that the sheer amount of effort that has gone into presenting this for our audiences. We're so grateful to the entire team. Thank you for taking the efforts. It was really brilliant, and the talk was extremely articulate. And we have so many questions lined up for you. And I'm sure there will be more in the post-interaction session. So we'll take the remaining questions there. But let's get started. So there's a comment from the attendee that they said, I've always wondered why we attempted making humanoid robots. These experiments map solutions for humans. Thank you for the close-in display of robots. So the one question that we have here is, have these robots gone out into the market or are they still in the research and development phase?
So there are various forms, as you correctly point out, there are various forms of these robots. So there are a significant number of robots that are now in the market. So you've seen some very good examples of robot vacuum cleaners from maybe 10, 12, 15 years ago. Now we're getting to a stage where robots like the Spot Mini from Boston Dynamics, which is a quadruped robot, which has the ability to move around and articulate things and inspect. There are other robots. So I would say an autonomous driving car is a kind of robot in the sense that it is got sensors, it's got wheels for actuating. It doesn't have any limbs for changing the state of the world, but it is able to navigate in a complex environment like a road. So in my sort of definition of robots is rather broad. And so from that perspective, I can say that there are robots that are now coming out into the market that are affordable and are providing good solutions, affordable solutions. Yet, there are things like humanoid robots are still quite niche in the sense that we see humanoid robots being deployed in very specialist environments, healthcare, or in scenarios where, for example, in the space station, where the environment is built for the humans, and so we would need articulation very similar to what a human would do. But yet I would not say humanoid robots are mainstream as in being a product.
Thank you so much. You're absolutely right. There are so many robots out there. Some are already out there, but like you mentioned, humanoid are not very mainstream yet. So I think you've already touched upon this in your talk, but can you shed some light on the application of robots in space research? Maybe an example here and there?
Yeah, absolutely. So I can tell you what is happening now and what the plans are and what the futuristic plans are. And this is typically a sort of pipeline for any robotics research. So what's available now and what is being used for now is indeed, so if you look at the Canada arm, which is part of the articulation system within the space station, which is used to do things like repair of the outside of the space station, but also pull and push various parts of the modular structures of the space station. So that is already a robot that is being used to maintain, build, repair, do things like docking and undocking of stations in the space station. Now, with the success of the Mars mission, we've seen some very good examples of, for example, a very good frugal mission from the Indian astronauts, the astronomy team, to Mars, but also many other countries attempting to land rovers and active systems, including the first flight on Mars recently. So first small helicopter in the Martian atmosphere. So we are now seeing stages where there is a possibility, if one wants to create a sort of working environment in another planet, like the Red Planet. There is also an ambition to put stuff, put a station again on the moon as a kind of, it's called the slingshot version. So in some ways, what we are seeing is the theme is consistent. We are looking at robots doing jobs that are dangerous and risky for humans in environments that are extreme. So radiation, sort of deep things with space debris, etc. But also doing support activities for astronauts. So it's not like the robots are there to try and replace parts of the space exploration, but to be able to support the astronauts and make things a lot more cheaper and do trials ahead of time. So proving grounds, I would say.
Thank you so much. I think that was really articulate and insightful. Professor, what we do is maybe take one question here and then move into the next post-interaction session. But we have a question here that says, have you worked on inculcating consciousness in robots?
So it's an interesting question, and luckily I've been in a very lucky position to work at the bridge of human neuroscience, computational neuroscience, and motor control and robotics. And this is reflected in the science that we do, because while we look at robots in factories and extreme environments, we're also looking at robots for healthcare, for being sort of for the use of exoskeletons, prosthetics. We're also looking at projects related to robot scrub nurses in sort of surgical environments, etc. So indeed, the challenge of sort of bridging this thing between what we call intelligence and learning and adaptation, and where we call those changes or adaptations that are rules that have not been written by the programmer, but things that have been evolved and adapted from behaviors and data. And when we start calling that intelligence or consciousness, is a fine line. So I think everybody has a different definition of consciousness and bias and intelligence. So it's very hard to say conclusively whether I've worked on consciousness or not. But what I can definitely say is I have worked on systems that have tried to build intelligence or adaptive abilities, if you call that intelligence, into artificial systems. So we can expect behaviors that evolve, change from things that have been programmed based on sort of value functions and cost functions. So in that sense, yes, but I would still say that the notion of consciousness, whether be consciousness in animals, consciousness in plants, consciousness in machines, it's a gray area, and it's something that we always think about, but I don't think any of us have got conclusive answers to it.
That's absolutely right. I mean, we had a talk on the neuroscience behind consciousness, and neuroscientists spoke about the various areas of research. I mean, we don't have any conclusive answer. There's just many theories that we're working on. But Professor, we have more than 15 questions lined up, one on the applications of nanotech in robotics, the mechanical aspects of the humanoid structure, your work in artificial intelligence, your work in robot wars. So we're going to take all of these in the post-session interaction. I can tell all the attendees that you'll find a link in the chat right now. We'll drop it a couple of times. We'll request you to move to that meeting where you can personally ask Professor all of your questions. But a very Big thank you to you, Professor, on behalf of the entire team at India Science Festival. We're so grateful to you and your team for taking out the time. It was an absolute pleasure, and we really look forward to hosting you at ISF in the coming years in an on-ground setting where you're able to come to India and interact with all of our attendees on a closer level. So we really hope that will happen in the coming years.
Absolutely, it was a delight, and thank you for all the questions, and thank you, Shruti, for this organization. It's an important and a very, very, I would say, crucial element in the development of Indian science to do these festivals, and I wish you all the best for all the future events as well. So I'll see you in the other chat room, and thank you all for attending. Bye.
Hey!